Good afternoon, everyone. My name is Shannon Underwood, and today I'm going to be presenting my undergraduate thesis project results, which is on the effects of building height and plant selection on extensive green roof pollinators. It is co-authored by PhD student Nicholas Sukin and Dr. Scott McIver from the University of Toronto Scarborough campus. Green roofs are a type of green infrastructure, and it is defined as a roof that is covered in vegetation, which has a waterproof membrane and a growing medium. Green roofs are commonly implemented worldwide because they offer various benefits, and they've even become policy in some cities, such as in Toronto, that mandates green roof installation on any building that is greater than 2,000 square meters in floor area. Green roof implementation is largely driven by their primary functioning, which offers stormwater management, building insulation. They help to improve air quality, and green roofs even help to moderate urban heat island effect. There are two types of green roofs, intensive and extensive green roofs. Intensive green roofs generally have deeper substrates and thus can hold a greater number and more diverse plant species, whereas extensive green roofs have shallow substrates and thus can only support small and shallow rooting plants such as succulent species and grass species. Extensive green roofs are typically the most commonly type of green roof that is implemented onto buildings because they're inexpensive and lightweight, making them easily deployable and adoptable worldwide. As extensive green roofs are limited in their plant selection, most have become heavily reliant on the use of succulent flowering species from the genus Sedum, and so Sedum-dominant green roofs have become a quite ubiquitous sight. Over the recent years, green roofs have become highly promoted as a potential tool in pollinator conservation because they extend natural habitat available from the ground level, specifically in urban areas where there are more buildings than natural green spaces. However, pollinator dispersal to green roof sites may actually be limited by building height of the roof. Despite being highly mobile, many pollinators may be limited in flight ability. For example, Greenleaf et al. 2007 researchers demonstrated that bee flight distances were positively correlated to their body size. More intense wind is also experienced on taller buildings, so for some pollinators it may not be worth it to invest the energy to fly vertically to forage for food or habitat, especially since green roofs offer limited plant diversity. Pollinator green roof studies are new and up and coming, and there's a lot more work that needs to be done, but most of them show that green roofs are accessed by a diverse group of pollinators. Kola et al. 2009 and Drumgold et al. 2020 both report similar communities of pollinators to access ground level and green roof sites. Comparatively, Tonetto et al. 2011 researchers reported a lower abundance and diversity of bees to be on green roofs than their ground level sites. They also show bee diversity on green roofs to be positively correlated to local plant diversity and composition. While Krashmer et al. 2018 found that the number of flowers in bloom available on green roofs highly predicted bee abundance more than plant species richness did. It is quite evident that there is a need for more pollinator green roof studies in order to better understand how green roofs actually contribute to pollinator conservation. And our study was most interested in understanding the effect specifically of vertical isolation and blooming amount on pollinator abundance and richness, in addition to assessing if sedum and non-sedum flowering plants supported different pollinator communities on green roofs. We first hypothesized a decline in pollinator abundance and richness as building height of the green roof increases. Secondly, we hypothesized an increase in pollinator abundance and richness with increasing blooming amount. And thirdly, that sedum and non-sedum flowering plants would attract dissimilar visiting pollinator communities. Our experimental setup was around the University of Toronto Scarborough campus, and it included a total of 6 green roof sites that varied in height of 6 meters to 20 meters, in addition to 2 ground level sites that were used as controls. We had 45 singular modules that were arranged like seen in the bottom right picture. 32 of those modules were seeded with 4 sedum species, and 16 of the modules were seeded with the non-Sedum flowering plant Rudbeckia hirta. To record the bloom amount of our flowering species, we counted the weekly yes or no presence of flowers in bloom on each module across all of our sites. To be counted present, the species had to have at least one flower in bloom on the module. And during analysis, we tested the weekly percent Sedum and percent Rudbeckia occupancy as predictors of weekly pollinator groups' abundance and richness. I hand sampled any bee, fly, or wasp that visited a flower on our sites during 15-minute surveys per site that was performed once per week between May and September of 2019. These surveys were conducted only on sunny and non-windy days. We performed all of our statistical analyses in R programming language. We first used generalized linear mixed models to assess the effects of building height and the percent occupancy of Sedum and Rudbeckia for pollinator abundance and richness, and this was performed for total pollinator, bee, fly, and wasp groups. During our analysis, we found two distinct blooming periods. Period 1, which is characterized by the Sedum bloom between June 23rd and July 28th, and period 2, which is more characterized by Rudbeckia hirta bloom, which is between July 28th to September 22nd. We decided to assess the effect of building height and percent occupancy of the flowers on pollinator group abundance and richness per period. Secondly, we used Spearman's correlation to assess the similarity of pollinator communities visiting Sedum and Rudbeckia in order to better understand their contribution to pollinators. We additionally used Levine's measure of niche breadth as a mechanism for estimating the extent of which pollinators visited each flower species. And then finally, we used a bipartite graph to visualize our plant pollinator network across all of our sites. In total, we collected 147 specimens. 59 of those were bees for a total of 18 bee species, 69 flies, a total of 3 fly species, and 19 wasps, a total of 5 wasp species. Our second ground level site was the most abundantly visited site, while the most visited green roof was the lowest to the ground, which was our 6-meter site. And I just also want to highlight that we had no visitors to our tallest building green roof, which was our 20-meter site. We found that pollinators total and bees were negatively correlated with increasing building height during both periods, which supports our first hypothesis. Observationally, pollinator total abundance appears to be strongly driven by the trends in bee abundance, which can be seen on the graph on the left. We found the same to be true for pollinator richness, in that pollinator total and bee species richness decline with increasing building height. And again, it appears that bees drive the trends in total pollinator richness, which is seen on the graph on the left. We only found some support for our second hypothesis that we would see an increase in pollinator abundance and richness with increasing floral amount. The graph to the left shows the pollinator visitor abundance on the right, while the occupancy of Sedum and Rudbeckia on the modules per week on the left. The only significant correlations we uncovered were bee abundance and richness, wasp abundance, and pollinator richness being positively correlated to increasing Sedum occupancy during the first period. No pollinator group was correlated in abundance or richness during period 2, which was characteristically the Rudbeckia bloom. After performing Spearman's correlation, we didn't find evidence that Sedum and Rudbeckia were visited by dissimilar pollinator communities, instead that they were only intermediate in similarity. This graph visualizes the Spearman correlations that we conducted. With increasing intensity of the blue, and the larger the circle is, means that the pollinators visiting each of the flowers is more similar, while increasing intensity of red and larger circle means that flower visiting pollinators were more dissimilar. And among each of the sedums, we see that they're visited by quite highly similar pollinator communities. Rudbeckia hirta was the only group that showed some red circles, although because the correlation R values were between 0 and negative 0.19, the dissimilarity is deemed negligible. And thus we cannot conclude that Rudbeckia and Sedum support different pollinator communities. However, these results still demonstrate that seeding Rudbeckia onto sedum-dominant green roofs can benefit pollinators by extending the floral availability for some. Interestingly, one of the sedum species yielded the greatest measure of Levine's niche breadth, which again in our study measures the width of pollinators visiting our flower species, and that is Sedum kamtschaticum, which had a breadth of 6.81. Following this was Rudbeckia hirta, which had a breadth of 4.45. The most abundant pollinator visiting sedum was Toxomerus marginatus, which is a native hoverfly species, while the most abundant bee visiting sedum species was actually a non-native species called Anthidium oblongatum, and this raises some potential concern over sedum disproportionately supporting non-native pollinators over native pollinators, and this is also highlighted in a study done by McIver et al. 2014. For Rudbeckia hirta, the most abundant flower visiting species we found was to be a native bee called Halictus legatus. In all, we found building height negatively impacted the abundance and richness of some pollinator groups that we studied. We found that sedum coverage, so the percent occupancy on extensive green roofs, was an important factor for the abundance and richness of some of our pollinators. We showed that sedum and Rudbeckia flowers were both valuable resources to green roof pollinators. Additionally, the seeding of Rudbeckia hirta onto our sedum-dominant green roofs allowed for the extension of the blooming period of the roof into the later season of August, which is an important consideration for pollinators that are active during different points of the season. And finally, we found that Rudbeckia hirta and sedum species supported intermediately similar pollinator visitors. We highly suggest that any future pollinator green roof project prioritize low-rise buildings for habitat, and that they integrate sedum with non-sedum flowering plants onto the green roof. We also just suggest that they intentionally choose flowers that have complementary blooming periods to increase the access of the roof to a diverse group of pollinators. I want to acknowledge that this project was funded through an NSERC Discovery Grant that was awarded to Dr. Scott McIver. I want to thank the Department of Biological Sciences at UTSC for hosting an undergraduate thesis program that allowed this project to be possible. I want to thank the management staff at UTSC for giving us access to green roofs to perform this experiment. I want to give a special thanks to Nicholas Sukin and Dr. Scott McIver for their invaluable contributions to this paper and to analysis. I want to thank Julie Wang and Adriano Roberto for green roof maintenance. I want to thank Dr. James Hung for his aid in species identifications. And of course, I want to thank our pollinators for everything that they do and for their contributions during my project. Finally, I want to thank you for listening and for your time. If you have any questions, feel free to contact me. Otherwise, stay safe.